There are several methods available to us when we want to perform analysis of indeterminate structures without making the assumptions we made in previous chapters. If the structure has only 1 or 2 degrees indeterminacy, then a very efficient method is the force method. And so we'll use that method to analyze an indeterminate beam in this example. The key concepts we'll cover are calculating the degree of indeterminacy, selecting a redundant for the force method of analysis, and predicting deflection of a beam. And here's our problem. We have a beam with uniform load. It is fixed at end A and a roller support at B. We want to determine all of the reactions, and we'll consider the modulus of elasticity and the moment of inertia as constant along the length of our beam. And our approach. We'll start by approximating the answer. So that we have something to compare against once we've performed our more lengthy calculations. We want to be able to evaluate the reasonableness of those results. Redundant. Then we'll figure out how many degrees indeterminate it is, so we can figure out how many redundants we need. We'll choose those, and we'll write equations of compatibility for each redundant. Then we'll find deflection of the primary structure, deflection of the primary structure due to the applied loads, then we'll find the deflection of the primary structure, which is another way of saying the released structure, the structure without the redundants, due to a unit redundant. Then we'll be ready to combine that information with the equation of compatibility to find the redundant. Then we'll find the remaining support reactions, and we'll compare with the approximation. So let's get started. We'll begin by finding an approximate answer. To do that, we'll take it in a couple of parts. I'm going to start by talking about the vertical support reactions. And here's what we're going to do. Let's assume load is carried by the nearest vertical support. That's going to mean that with AY and by, and a distance of 15 feet, and a distance of 5 feet, all the load in this region will go to by. All the load in this region, 7.5 feet, will go to by, and all the load in this region, 7.5 feet, will go to AY. And the load we're talking about is the uniform distributed load. So my approximation of AY will be the distributed load times the 7.5 feet. So my approximation is 3.75 kips acting up. by, I'll approximate by taking 0.5 kips per foot, 7.5 feet plus the 5 feet. Put those all together and I'll get a 6.25 kips up. Now let's talk about the moment support reaction. If we modify the geometry so that we have fixed at the end and support at the other end so that this is 20 feet, with our uniform distributed load of 0.5 kips per feet, my moment reaction, MA, will be bigger than in this situation, the real situation, where the support is closer in, because we have more distance in which to sag. Now, it won't be as big as if it was cantilevered with no support, but this provides an upper bound on the moment we can expect. And this is a special case that we can find in the back cover of our text. So if you have not explored that part of your book yet, there are indeterminate structures shown in the back cover, and it has pre-calculated the moments at the ends of those special indeterminate beams, called them fixed end moments. And so we have the situation we just modified into shown right here. The moment reaction will be counterclockwise omega L squared over 8. So we have MA will be approximately, in this case we drew it in the opposite direction, so it'll be a minus omega L squared over 8, a minus 0.5 kips per foot, 20 feet squared over 8, which is equal to a minus 25 foot kips in the clockwise direction. So it's not in the clockwise direction. So we know that we should obtain a smaller quantity than this. Now let's apply the force method. Now step 2. We're going to figure out how many degrees indeterminate so we can figure out how many redundants we need. And for each redundant, we're going to write an equation of compatibility. we have vertical reaction at A, a moment reaction at A, horizontal reaction at A, and a vertical reaction at B. So to evaluate our indeterminacy, we look at our number of unknown support reactions, which is 4, and subtract the number of free bodies, 1, 3 equations of equilibrium per free body. It's 1 degree indeterminate. Therefore, we need 1. We have 1 redundant. We need to identify which one we want to call the redundant. And so now let's choose that redundant. It is my choice. I can pick anything to be the redundant as long as it leaves me with a stable structure. But some choices will make the calculations easier than others. In this case, I choose BY, because when I remove BY, I have a cantilever, and there are formulas already predetermined for us in the front cover of our text that can help us predicting deflections. Our equation of compatibility. Let's draw our primary structure, which is now the cantilever with uniform distributed load of 0.5 kips per foot. And this primary structure will deflect like such, and at B we can calculate the deflection. We're talking about a superposition of loadings. So again, I have the primary structure, but in order to get back to the original, we're going to take BY and amplify the response of this cantilever when we have a unit force act at B. And that will give us a deflected shape that looks like such. And over point B, we have a deflection that we'll call the flexibility coefficient, or FBB. The deflection at B due to a unit force applied at B. Together, the summation of these two has to produce a net deflection at point B of 0. So the displacement of the primary structure due to the applied loads, in this case the uniform distributed load, plus the behavior of the primary structure with a unit redundant amplified by the quantity BY, have to add to 0. And that's our equation of compatibility. Now that we have our equation of compatibility, we're ready for step 3. Let's predict deflection of the primary structure, in this case the cantilevered beam, due to the applied loads, in this case the uniform distributed load. Primary structure is a cantilever beam the uniform distributed load. And it will deflect downward. And produce a deflection at B we'll call delta B. Now if we look in the front cover of our text, we'll find over a page of different situations. One of them is cantilevered beam with uniform distributed load. And we don't need the deflection out at the end, we need the deflection over here partway across. So we'll use this formula for deflection where x starts at the fixed support end. So if we start our calculations from A, we get a formula for the deflection at B of minus the distributed load, omega, over 24 EI times the distance to the point where we want to calculate displacement, that's B, raised to the fourth, minus 4 times the overall length times that x distance cubed plus 6 times the overall length squared times the distance to the point squared. This formula, by the way, was obtained by applying double integration to a cantilever beam. So this equals a minus 0.5 kip per feet over 24 EI, 15 feet to the fourth, because it's 15 feet from the support, the fixed end, out to point B, minus 4 times the overall length of 20 feet times the distance to where we want to calculate the deflection, 15 feet cubed, plus a 6, the overall length 20 feet squared, and the x distance 15 feet squared. We evaluate this expression and we get a negative 6,680 kip feet cubed over EI. Now we're ready for step 4, where we predict deflection of the primary structure or the released structure, the structure without its redundant, and this one will be due to a unit redundant. So in this case, our primary structure is a cantilever. The redundant is a vertical force at B, and so we'll make that a value of 1. It will cause a deflected shape as such, and this distance we will call the flexibility coefficient BB. So in this case we're looking for a way to calculate that deflection. Let's go back and look in the front cover of our text again. We don't have a cantilever with a point load closer in than the end, but we do have this cantilever with the point load at the end. But I don't need to predict deflection beyond the load, I need to predict deflection at the load. So we'll be able to use this relationship, minus PL cubed over 3EI, as long as the L we use is the distance to the unit redundant. So we have minus p L cubed over 3 EI. That's going to equal minus, now we have to be very careful with our sign convention. We chose to use the formulas in the front of the text, and that means up is a positive deflection. The formula that we obtained from the front cover of the text here has P drawn down. So since ours is drawn up, we have a negative 1. Remember, it is the distance to the applied load, 15 feet. All of that over 3 EI. And this equals a positive 1,125 feet cubed over EI. And so this comes up with a positive quantity, which we would expect. If a positive deflection is upward and we apply our unit redundant upward, we would expect the flexibility coefficient to be a positive quantity. Now we're ready for step 5. Let's find the redundant. Our equation of compatibility is the deflection at B due to the applied loads on the primary structure is equal to the amplifier By times the flexibility coefficient, or vertical deflection at B due to the unit redundant at B, and those add up to 0. In step 3, we calculated delta B to be minus 6,680 kip feet cubed over EI. To which we add By times the 1,125 feet cubed over EI, and that adds to 0. Well, the EI's will cancel out, the foot cube will cancel out, and we'll get a units of kips for By. We solve that and obtain a positive 5.94 kips in the direction we had drawn it, up. Now we're ready for step 6. Let's find the remaining reactions. So we need to find AY, AX, the moment at A, and we already found that By is a positive 5.94 kips, or 5.94 kips up. So we'll apply equilibrium. Let's go horizontal equilibrium first. Choose to the right as positive, and our only contributor is AX, so it must be 0. Now let's sum forces in the Y. Choose up as positive. We have the unknown AY. We have the downward uniform distributed load acting over 20 feet. And we have the upward reaction at B. Solve for AY, and we get a plus 4.06 kips. So it is up as drawn. Now we're ready to sum moments. I'll choose to sum moments about point A. and I get to choose the direction of positive for my summation, and I'll choose clockwise since most of the applied loads are going to give us a clockwise contribution. MA is clockwise. The uniform distributed load gives us a clockwise contribution. Acting over 20 feet turns it into a force resultant, and that force resultant is at 20 feet over 2 from point A. We do have a counterclockwise contribution from the vertical reaction at B, and that is through 15 feet. Solve that to find MA is a minus 10.9 foot kips. We had originally drawn it as clockwise. It's not. It's the other direction. Now step 7. Let's compare these answers with our approximation. We had originally approximated AY to be 3.75 kips up, BY to be 6.25 kips up, and the upper bound on moment to be a negative 25 foot kips, so not in the clockwise direction but in the counterclockwise direction. So we'll re-rate that here. We estimated AY to be positive 3.75 kips acting up. We calculated using the force method of 4.06 kips. Those are reasonably close. BY we said would be approximately 6.25 kips up, and we calculated 5.94 kips up. Those are reasonably close. And we said that the upper limit on the moment at A would be a minus 25 foot kips, so not clockwise but instead counterclockwise. And we obtained a not clockwise, therefore counterclockwise answer of about minus 11. So it's less than our upper limit, but still reasonably close, about half the size. So by keeping the roller support or rocker at B instead of out at this far end saves us roughly half the moment at the end. So we'll say that those are reasonably close and that we have a reasonable set of predictions of our support reactions. Now let's go back and review the process we followed. We started by approximating the answer. We made one assumption in order to estimate the vertical support reactions, and in that case we said that the downward force would go to the nearest vertical support. And then for our moment support reaction, we modified the geometry by sliding the rocker from B out to the end, and noticed that that would be a more severe condition for moment at A, but that severe condition is available from the back cover of our text, pre-calculated, and we used it to create an upper bound estimate for the moment support reaction. To begin the force method, we had to calculate the degree of indeterminacy, in this case first degree, because the degree indeterminacy is the number of redundants we must identify. We could choose from a variety of redundants. In this case we chose BY because it let us use formulas in the front cover of our textbook to predict all the deflections we needed. We then wrote our equation of compatibility that brought the deflection at B back to 0. We then released the structure from its redundant support at B to get our primary structure, a cantilevered beam. We used the formulas in the front of our textbook to calculate the vertical deflection at a point other than the end of the cantilever beam. We then removed the applied load and applied just a unit redundant at B. To find that deflection, we went back to the front cover of our textbook and noted that although there is no cantilever with a point load away from the end, if all we need is the deflection at the location of the point load, we could still use the formula provided, just with a modified length. We then used that flexibility coefficient along with the deflection we calculated for the cantilever under the uniform distributed load in our in our compatibility equation, and we calculated the vertical reaction at B. We then used our three equations of equilibrium to find the three remaining support reactions. We compared them with our approximation and found that our results are indeed reasonable. Well done.